Hi everyone. In this video, we're going to talk about section 4.3 in Thomson's Modern Particle Physics book. Okay, so hopefully you have just saw the video on section 4.1 through 4.2 in the same chapter in the Thomson textbook. So those two sections will introduce you to the Klein-Gordon equation and also the Dirac equation. And then when we found the Dirac equation, it turns out to be these little interesting spinners that we have to deal with matrices. And I'll show you guys that in a second here, where we review the Dirac equation. But before we get started, I also like to take us back to Thomson's chapter 2.3.2, where he introduced this idea of probability density and also the probability current. Okay, so the probability density is basically the wave function square, well, psi star psi. Okay, if you were to try to calculate the probability of a particular particle in a particular position and time, what you would do is you actually integrate this psi star psi over some volume integral where your, this volume is in a place that you're interested in trying to measure this particular particle. Okay. And so pictorially, right, you imagine you have some volume down here, right, this little green blob thing, okay, and it can be any shape. It doesn't have to be this ellipsoid shape, okay, and there's a chance for your particle to be inside this volume, or there's a chance for it to be outside. I'm drawing multiple particles, but the idea is that probability will basically multiply if you have, let's say you have a 10% chance of the particle being inside that volume. That's basically the same way statistically you think about if you have 100 particles, what's the chance of finding 10 of them in there, right? But each of these little particles, right, can have, its own little trajectory flying everywhere, right, in some random direction. Okay, so it is possible for these particles to flow out of your volume. Okay, the way we quantify that is this probability current, right, J, right, that's what this is trying to symbolize, right? This is basically signifying, how are these particles flowing around in your system, okay? Or in the case of quantum mechanics, what is the probability of that one particle flowing around in some direction, okay? So if you look at this volume here, we already covered this when we talk about this in chapter 2, but if you think about this, right, whatever particle flows out of your volume, which is quantified by this little surface integral here, where J dot ds basically tells you if you have a particle flowing out. Let me just change that to purple. Okay, you have a particle flowing out here. That gives you some current flowing out of that particular little tiny volume. But if you integrate over all of the volume, meaning you do all the green surface here, okay, that'll tell you how many particles are flowing out of your volume. Okay, that's what this right hand side of the equation is showing you. Okay, we put a little negative sign because what's happening is that the left hand side of the equation is actually how does the probability of finding your particle inside that volume is changing. So if you're losing particle on the right hand side, in other words, J dot ds is a positive value, right? That means particles are leaving your particular volume, right? The negation of that, or the negative of that, tells you how does the probability of your particle being inside that volume changes with time. Okay, so there's a negative sign there because, right, particles leaving your particular volume will decrease the probability density of your particle being inside your volume. Okay, and using the divergence theorem, what you can do is you change this surface integral into a volume integral, and now you can basically think about this as these volume integral kind of canceling out. It's not exactly that, but what you can do is actually compare what's inside these integrals, right? You can have d by dt of partial by partial t of rho on the left hand side, and you have the divergence of the current on the right hand side. Okay, so what that tells us is that, well, whatever this stuff is going to be equal to this stuff with a negative sign. Okay, so therefore, if we put both these, put the negative of the divergence of the current to the left hand side, you'll end up with this equation where the divergence of the current plus the change in the probability density has to add up to 0, and this is known as the continuity equation. Okay, just write that down. Okay, it's just telling you that whatever particles flowing out, you're going to have a negative effect on the probability inside that volume, and therefore they're going to be equal but opposite each other. But then if you put them both on the same side of the equation, then they'll add up to 0. Okay, so what we're going to do is we're going to do the same thing, but with the Dirac spinner now. Okay, so the Dirac spinner, right? Let's start off with the Dirac equation, where the left-hand side of the Dirac equation is the time partial by partial t of your wave function, right? And then you have this alpha stuff here. So this is actually alpha dot p as the operator, plus the mass, right, gives you that psi. Okay, that's basically this representation, right, where you have alpha x partial by partial x. So this part comes from the momentum operator. This part came from alpha. Similarly with y, similarly with z, and then of course you have the mass. Oops, forgot the beta up here, of course. Okay, so if we kind of rearrange things a little bit, okay, what we can do, right, basically move this to the right hand side, okay, and only look at how distribute this this wave function through each of the term. And what we can do is then we can find the Hermitian conjugate of every term separately. So just have to be a little careful about this, because, right, these alphas and beta are 4x4 matrices now. They're not numbers anymore. So we have to be really careful with that. Instead of just taking the complex conjugate, we have to actually take the Hermitian conjugate, which basically flip all the indices on the matrix, and also make all the i's to negative i's. Okay, and speaking of that, so we have I going to negative i's here, right, and then all the negative i's in front goes to positive i's. Okay, and then the mass term doesn't have that, so we don't have to deal with that. Okay, one of the things that we're going to check in the homework is that, well, we want to make sure that alpha, beta are Hermitian. So this will be in the next homework assignment. Okay, that alpha and all these alpha and betas in the Dirac Pauli representation. So you can do this explicitly. You can find that they're going to be Hermitian, meaning their Hermitian conjugates are actually equal to itself. So all of these daggers just kind of goes away. Not that one. All these daggers just kind of goes away, right? So you're gonna have to deal with that. Okay. So that means psi dagger, right, times this equation. This is where there's a little bit of algebra steps. Okay, it's going to be equal to this equation down here. Okay, going back. Right, but then 4.15, which is up here, times psi, right, is going to be combined together. That's what this first equation is trying to get you to do. And then here's the purple one. Okay, that's what the second one is trying to get you to do. So this is equation. Let's just write them down here on top of here. Right, this is psi dagger times equation 4.14. And this is equation 4.15 times regular psi. Okay, so when you do that, what happens is that then you have both of these on, and you subtract the two. What happens is that then on the right hand side you basically have these two things added together, because the subtraction actually cancel out this negative sign here. Okay. Now we do a big reordering of things. Okay, what we can see is then, okay, this negative I, big parentheses, okay, psi dagger alpha x times psi dagger by partial x of psi, okay? And then the reverse version of it, okay, what we're going to do is we're basically combining, let's say, this term, right, with this term, just kind of squishing them together, okay, well, putting them next to each other. And this is going to look exactly the same for both the x and the y's. Okay, sorry, the x and the z, okay, not the, sorry, the y and the z, okay. The right hand side we just kind of keep the same. What we're going to do is we're just factoring out this I just to so that we don't have to deal with it for a little on both terms. Okay. Since the mass, right, m here is the mass of the particle, so that's a scalar. So remember that scalar can commute with anything you want. So you can actually pull this m out in front. Okay. So you can actually, oops, not that far. Pull this m out in front. And what you'll see is that, well, you have m times this thing, m times this thing, so these two are exactly the same thing. So this middle term, this term actually adds up to subtract to 0. Okay. The other terms, okay, can be simplified just using some chain rule from calculus. Okay. So we're kind of, what I'm going to do is I'm going to do this backward and just show you that it turns out to be exactly that. So if you take the chain rule, let's just do this on the right hand side here. Psi dagger alpha x psi. Okay, if we take the partial derivative of that with respect to x, okay, we're going to end up with, right, so the psi dagger depends on x, so we're going to have to do a derivative with respect to x with psi dagger, okay, and then multiply that by alpha x psi. Okay, remember that we're being careful not to change the orders of things since these are matrices. Okay, and then plus, right, because, right, alpha x doesn't depend on x at all. Alpha x is just some Pauli matrix, right? So, but then psi itself does depend on x again. So what happened is that you have psi dagger alpha x in front, and then you have to take the derivative with respect to psi. Okay. Okay. And that's what these equations are trying to show you. Okay. So what that means is that this term here, right, is exactly the partial derivative with respect to x of psi dagger alpha x psi. Okay, this 3 product thing. Okay. Similarly, you can find from just doing some little calculus by just taking partial derivative of psi dagger psi, you'll find that the stuff inside here is also the partial derivative with respect to time of psi dagger psi. Okay. Okay. So since this gives you the x component of derivative, then you're going to have the similar thing with partial by partial y. Then you have similar thing with partial by partial z, right? Okay. And what happened is that this basically becomes, right, the divergence of whatever is inside this argument. In this case, it's going to be psi dagger alpha, right, in the 3 component form, x, y, and z times psi. Okay. So that's how this big old equation up here, right, if you want to follow the big chain, becomes this. Okay. The right hand side becomes this, and the mass part disappears, right, because they subtract each other out, because the m actually can be pulled out of the multiplication. Okay. Now what we do is then, well, we're going to compare this to the continuity equation that we had in section 2.3.2, right, where, oh, well, we have divergence of j had plus the partial by partial time derivative of the probability density being equal to 0. We have very similar equation here where we have some divergence thing, we have some time derivative thing. By just looking at these two things, right, what you can see is that, well, this piece, right, has to be the current, and this piece has to be the probability density. Okay, and so we find that the probabilities for a Dirac spinor state is going to be psi dagger psi, and then the probability current density is psi dagger times these alpha matrices. Okay, the 3 of them. So there's an alpha x, y, and z. So you have a j, x, y, and z also. Product that multiplied by the psi, the 4 component, 4 element wave spinner. Okay. Yeah. So just a reminder, right? These are no. You cannot just do psi star here anymore because these are actually vectors, right? Remember that psi. That is now these 4 component things. 2 psi 3 psi 4, right? So just there's a lot of hidden things in here. Okay, so the probability density is actually going to be psi dagger psi, right? Where it's just the magnitude of each of the wave functions square. So unlike the Klein-Gordon equation, where we ended up with the probability density being proportional to the energy of the particle. Okay, and remember that sometimes this energy is negative, which gets you in trouble. In this case, right, it's just the square of the wave function all added together. That gives you the probability density instead. So you don't have these negative probability anymore, which is exactly what we want from a solution that is going to be both relativistic and obeys quantum mechanics.